Welcome to this evening's presentation, which is an introduction to duck color genetics. Just as a bit of preamble while people are joining, what we'll be talking about is the colors and the genes that form the basic patterns that derive in the sort of mallard duck stream, and starting at the basic wild type color of ducks. I just don't know why that moved forward, so we'll just go back one. So what we can see here as a start is the basic wild type mallard duck color. And I chose the duck to start the presentation because I think what she demonstrates is how in nature we have a color pattern that seems quite complicated, but anyone who has bred mallard ducks and seen a duck sitting in the straw, she's actually very well camouflaged. Now, the male has brighter colors, but what you can see there is what we would call the wild type duck color in the female. So it's very well adapted to a wild lifestyle, but over time, there's been a range of mutations that have changed the colour patterns that people have used either to breed new colours within breeds or are very characteristic of certain breeds. So we'll touch on how those mutations work and how they interact with each other. What I'll do is just spend a couple of slides going over some of the basic principles of genetics as a bit of a refresher. I know some of you will have listened to my previous talks on landfowl genetics, and some of the principles are the same, but for those who are joining new with respect to waterfowl, I'll go over those, and then we'll touch on, as I said, the basics of duck colour and how the genes interact and what some of the genetic basis of some of the distinctive colour patterns are. We won't be able to cover everything because of time, and so I think you need to see this as an introduction or a refresher. And I'd just like to say that I am not the world expert on duck colours, so I've been learning as I go here. But one of the things that I see when I judge waterfowl here in Australia is that, particularly with the advent of increased classes of call ducks in Australia, people are creating lots of new colours, and sometimes they get it right and sometimes they get a little bit wrong. And in some of the cases where they've got it a little bit wrong, an understanding of the basic genetics would help. So what tonight is about is really taking the first step to understanding duck genetics. So just like the white mallard here, we're about to step into the world of duck genetics. There are some terms that I will use throughout the presentation, and again, I've covered some of these in previous talks, but we just need to refresh ourselves about them. So we talk about chromosomes, and in simple terms, a chromosome is an assembly of the DNA, and you can see it as a linked group of genes. And sometimes that linkage matters because sometimes genes are on the same chromosome, so they get inherited together, but usually with what we're talking about here, they get inherited independently of each other. The next thing we talk about is the gene, and that's really a coding region of the DNA. So when we say coding, we mean that variation in that DNA causes a change in function. And the change in function we'll be talking about tonight is a change in the way the color is deposited in the feathers. And it's important to remember that the genes act in pairs. And so almost always the duck or drake has two copies of the gene, and how they interact determines the color. There are a couple of differences, and we'll touch on those in the presentation. The other one is a bit more of a scientific term that we don't tend to see much when in the hobby form of genetics, and that's locus. And what a locus is really the location of the gene on the chromosome. So we most often, if I was at work talking, we would talk about the um, brown locus as the location where the gene that codes for brown is. The other aspect that we talk about is an allele, and an allele is a variant of a gene. So if we think about the uh, blue gene, that's one variant. The other variant is not blue. So we can talk about that. And we need to remind ourselves that genes are either dominant or recessive. And so this is the alleles of the genes are either dominant or recessive. And so that means that one form dominates, as the name suggests, over another form. And sometimes this dominance is complete, and so it completely masks the effect. The other is sometimes it's incomplete, so you'll get an intermediate phenotype, which is another term I should have put there, by the way. And phenotype just refers to what you see. Genotype is the genes that the animal has. So we often hear a term about build the house, then paint it. And what this term in exhibition breeding usually refers to is get the type right and then add the paint colors, which is the. With this duck genetics presentation, I'm actually saying there are two series of genes that actually should be considered to be part of the house when it comes to duck colors. And unfortunately, if you don't get a basic grasp of these foundation color genes or pattern genes, it gets really hard to understand more complicated patterns of duck colors. So the first I'd like to touch on is one called the Mallard series. And we can go through this side of the table here and I'll just activate my pointer so you can see that. Here we are. So the Mallard series here, and it can remind us a little bit of how genes work. There are three variants, so three alleles of these Mallard series genes. There is the mallard itself, and just to introduce this coding, M for mallard, a capital M means that it's a dominant variant over some other genes. And the little plus symbol here, which we should always use, but even me in this presentation tonight, I haven't always, refer to the wild type. So this is the variant that we see in that wild colored mallard, and then there are the mutations, so they don't have the plus symbol in genetics convention. We have the mallard restricted allele, which again is dominant over the next one, so it has a capital M, and it has this little superscript R that denotes that it's a variant of the gene to the wild type version, and what it limits is pigment, but it does tend to leave sections of white in the multicolored pattern. And the third allele is one called dusky. It's the recessive allele series, so it has a lowercase m here and a little d for dusky. And what dusky tends to do is remove eye stripes. It removes the scarlet chest color of a male, and we'll see that in a moment. But you have those three variants or alleles of that mallard series, and they then interact with what are called the phase genes. And so the phase genes are dark, which is the wild type, light, and so light causes a lighter color overall, but the specific effects will vary depending on the background. And then there's also the harlequin phase, which is another recessive gene, but a variant really of light. So what we see then is these pattern genes interact with each other and other genes to impact the color of the duck. So after this presentation, either in a book or in some online resources, if you're serious about breeding multicolored ducks, it's worth spending a moment to go through these. And it can be quite confronting, but once you, hopefully with some of the examples we'll look at, I can help take some of that out in this introduction. What is important, and this is something that I touched on in the preamble, is not all combinations result in standard colours, no matter how nice they look. And this is one of the things that we see when we're judging. You get these nice coloured ducks, but they're not actually a colour. And from time to time, a judge will say, well, it's not really any colour. The type's good, but it's due to the having not the right basic profiles of these genes and how they interact. And the other thing that I want to say just when we get into this is that impure, so when I talk about impure here in a hobby term, I'm referring to what a scientist would call heterozygous. So if you had one copy of the mallard gene and one copy of the dusky gene, or one copy of harlequin with one copy of light, some of these impure combinations result in color faults. So when people have been crossing colors, some of the inconsistency we see is that they're not yet pure for these basic genes. I just want to touch on, and I know from the experience that people do watch these presentations in other countries, I'll basically be using Australian nomenclature because that's what I know more or less. I know that, you know, in the United States, for instance, you have a lot more call duck colours than we have over here, and sometimes they get called different names. So rather than get things wrong, I'll stick to what I know, but the basic genetic codes are the same, and hopefully you can make some interpretations. So I just want to touch on that. And so here we have the wild type mallard, so M plus, and these are classic mallard colors. So as I said, the duck who's very well camouflaged, the male who has a bit of color, but in the eclipse molt does revert back to a much more simple color pattern and more camouflage color pattern. And so it's how the mutations affect this basic color pattern that we'll be talking about for the rest of the presentation. So the next allele that I want to talk about when I'm just talking in the mallard series is the dusky allele. And so you can see the effect of a dusky here. So this is a dusky mallard drake. What you can see is having two copies of this dusky allele because it's recessive. What he has is he's lost the chest color here, he's lost the neck ring, and the duck herself tends to be a slightly darker color. But what you can see now is if you think about how these two different color patterns may exist in other breeds of duck, you can start to think of breeds of duck where the drake has the green head, no chest color, no neck ring, might actually be because that color or that breed is based on a dusky background. So it just gives you an idea when you start to see these things as to what the genetic basis of different breeds are. The next allele, and unfortunately, is the restricted one, which I said tends to make the bird lighter and also keep the areas of white. But I had to bring in, to get a good example here of the effect of the restricted mallard, the phase gene. So this is actually the light phase, whereas the previous birds were dark phase. And the classic example of a restricted mallard with the light phase is the Appleyard duck. I couldn't find a good example for you of that with the dark phase. So I had to bring in that same gene. But what you can see there is generally lighter color and the white elements of the color remaining. So you've actually got two mutations at play there from the basic mallard color, the mallard restricted allele at the mallard series, and the light phase coming in. If we look at this though, to think about that in terms of how colors and they sort of these genes interact to get the pattern, I want to go back one step and put the wild type mallard in and say, well, what is the light phase of the wild type mallard? And the light type phase of the wild type mallard is the color we call trout in Indian runners. And so you can see that effect there. So uh, what you can see already is that the effect that the light gene has depends on which allele it has, but also which background it's interacting with. So again, you need to have think of these two genes together, what you have in each of these genes, and then how they interact. So that's why I really said for multicolored duck patterns, getting a basic understanding of these genes and how they work in their pure forms will give you an understanding of how, should you decide to cross colors or try and improve a new color, having an understanding of that will actually help you get things right and not end up with these off-colored types that are no color at all, really. Just my computer is stalling for a moment, so I'm just may need to go. Just bear with me while I work out while it's not scrolling forward. There we go. I'll just go back to check that I didn't do a couple of slides, a classic lecturer's mistake. So now what I want to talk about is a set of genes to go through and how they, again, work with the different backgrounds or mask the effect of the backgrounds. So one simple gene is white, and white here is recessive. And the reason it's C is because it's color versus not color. So some of these names are historic and don't sort of make sense, and those conventions sometimes also exist across different species. So if you have two copies of this white gene, which is recessive, so you need both copies to see the effect, what you get is all of the color is hidden. Now, this white mallard drake here is most likely this drake and this color with two copies of this white gene. The truth is we don't know, but we make that prediction. And when you think about crossing white birds with colored birds, one of the things is that you will unmask what color is underneath this white. But you can think of this really as a coat of white paint on top of the colored bird. If you put two coats, so the two colors here, you've basically masked what is underneath. And whilst the example here is of mallards, this is actually true of all of the white birds in the mallard derived breeds. So tonight's talk, I'm not going to cover Muscovies. They have some genes the same and some different, but for the purpose of time, we'll be just talking about the non-Muscovy domestic ducks that we see in exhibition. The next gene that we can talk about is one we call extended black. And extended black is a dominant gene, so you only need one copy of it to cause this effect. However, I would expect that from time to time, some of the leakage that we may see of colours in blackbirds is because we don't have two copies of extended black, but it is quite dominant, so you should expect that you will get the colour underneath to be masked. So again, these drakes that we're looking at here, either as a Black East Indie or a runner, are actually have other patterns underneath, but they're masked by the black. So again, if you were to cross these and break this down and then cross again to remove the extended black, you would find out what color is hidden underneath here. The other thing about black in ducks is that the expression of the gene can vary from feather to feather, but also as the birds get older. And anyone who's bred black ducks knows that there's a trend to see them get whiter with age. And that's just a function of how the gene works. You can try and do something about it, but it's a general trend. So if you are judging the black runner class and you're in the old ducks or the old drake section, you can expect to see the odd white feather. The next gene I want to touch on is one called the blue dilution. And so it's basically blue called dilution because it dilutes black. And the classic breed we can think about with the blue dilution is the blue Swedish, as we have here. It also has a bib gene that we'll come to later. But blue in ducks is like blue in chickens that we did in a previous section, that the blue itself is dominant, but it's not completely dominant. So if you have one copy of the blue gene, you will turn into the blue. If you have two copies of it, you have this splashed silver phenotype here. I don't want to call it silver because silver in ducks has another genetic basis, but is sometimes called silver. But so if you mate this bird and this bird together, you would get all blues. And so this factor about blue is important in some other breeds that we'll come to later, but blue in chickens and ducks behaves the same way, and it explains why if you mate two blue Swedish together, you're going to see these colours in the offspring, because this bird, because it only has one copy of the blue gene, one copy of the not blue or black, when you cross them together, you would expect half the progeny to be blue, half to be black, and half to be the coloured phenotype. The other aspect of blue and how it appears in duck colours, we can see with this example of the mallard colour series here. There's a couple of mallard pictures and cold pictures, but the principle's the same. So here we have the wild type. So this is not blue in this case. So it has the two copies of the not blue version, the black version. When we have a blue or blue fawn here, we have one copy of blue and one copy of not blue or black. And then we have a form of apricot, and there are various ways that other genes can interact in the sort of apricot series. But basically that splashed bird, so the two copies of the blue, in this mallard type bird becomes what we would call apricot. So what you can see already is that the way blue affects on a coloured bird versus a solid coloured bird has a different effect and is important in how some of these different coloured birds are bred and whether they're going to breed true or not when you mate them together. The next gene that I want to introduce tonight is one which is the white bill or white skin gene, and it's actually a dominant mutation over the wild type. So we have a mallard drakes here, one with the wild type, which is the yellow bill, the other with the white or pink bill phenotype, which is much rarer here in Australia at least. But this white bill gene is also the same bill that we see in Aylesbury ducks, for instance, and would be part of the colour pattern difference between an Aylesbury and a white ruin. Obviously, the type issues and other things come in, but you can see here the effect is both on on the bill colour and the skin colour, which we can't see, obviously. The other thing that I think is quite interesting when you compare this to chicken genetics is that the white leg, white skin gene effect is seen in the legs in chicken as well, whereas in the duck here, what we can see is that the orange leg color remains in both variants. Another gene I just want to introduce, and I'm going through them one at a time with examples, trying to mix the breeds up a little bit, is one that's called runner pattern gene, or sometimes the pied gene. And what we can see here is that having runner pattern gene will convert a fawn runner into a fawn and white runner. Again, there are differences around the world as to what the genotype of a fawn and white runner is, but from our Australian perspective, I think the key thing to remember is that you've got the runner pattern gene. So what you can see is you have restriction of the color on the neck and the wings here. And we also see this gene sometimes, I believe, popping up in some of our call duck colorations, and I'll touch on how it interacts with another gene um, in a short moment. The next gene I want to introduce is the bibbed gene, and there are both dominant and recessive forms of this gene in the literature, and I have never bred bib ducks, and I have to say that I don't know if both forms are here in Australia. I think they are from what the bit of reading I've done, and I don't know which is the more common. But depending what you can, in general terms, they both act the same way in that you get the white bib here that we've seen on this call duck, but we also saw on the blue Swedish duck earlier. And if you wanted to know what form you had, it's just a matter of doing a test cross. If you have the recessive form, if you cross the solid bird here with the bibbed bird and you had a dominant, if you have a recessive bib to start with, sorry, so I'll just start that again. If you have a recessive bibbed form and you cross this solid breasted bird with the bibbed one, you would never see the bib in the progeny. If you had the dominant form of the bib and you crossed it to the solid bird, you would see some bibs in the progeny, and you would either see all bibs if this bird was pure or homozygous, or you'd see 50-50. So if you hatched enough ducks, you'd get an idea. So that test cross would tell you how it was operating. I have seen instances with people breeding calls saying, oh, we were surprised that the bibbed ducklings came out because the parents were solid, which suggests that they had the recessive form in those call ducks and the parents only had one copy. So when those two copies came together in the progeny, then you saw the bibs in the progeny that you didn't see in the parents. The next gene I want to talk about is the brown dilution, and the classic example I think of how the brown dilution might work or does work is taking from a dark Campbell pattern to a khaki Campbell pattern. So what you can see is it just lightens that bird's color down dramatically, and it's actually a sex-linked gene. So what this means, and I did a whole presentation on this sex linkage in poultry breeding a couple of weeks ago, is that the female can only have one copy of this gene and the male can have two. So you can have instances that you will get some segregation in the progeny, or you could use it for a sex-linked cross. So, but the brown dilution is important in a number of breeds, but it explains the difference between a dark Campbell and a khaki Campbell. Here is another example of the brown dilution at work, and probably more common in Australia is the fact that on a black-based bird, the brown dilution, when it's present in a homozygous form, so without any of the not brown or black in this case, is you get chocolate. And so this is one of the reasons why people who breed chocolate runners here often have black runners with them as well, and the populations are sometimes mixed, and the brown progeny or chocolate progeny in this case can pop out of those black lines when the males particularly are carrying the brown dilution to cause chocolate um, phenotype or characteristic here. So same thing if you think about chocolate cordrake, ducks or others, but you can see that this is the effect of the brown gene here on a black background is to turn the black duck into a chocolate duck. So I now want to just try and bring some of it together, and I know we've introduced quite a few genes in. I've just got a comment saying, looks like we've lost Kevin. Can someone, I've just seen that, that might have sat there for a while. Um, can someone just give me a heads up if you can still hear me? Okay, well, I'll just continue anyway, and hopefully you can. Facebook is telling me I'm still live, so we'll just keep going. Is that what I want to do now is go through with respect to some of the genes, some of the genotypes of some of the breeds with particularly characteristic patterns. So if we see here, this is an Orpington, which is on a D base. So as you would expect for a dusky, we don't have a neck ring there. We don't have chest coloration. It's a dark phased bird. It has a mutation that I haven't talked about, which is buff, which is a sex-linked gene and acts similarly to the brown dilution we just saw. And it is blue. And one of the things that the reason that it's important that it's blue is that you'll see that sometimes, well, if you are breeding exhibition Orpingtons together, this brown head on the male, sometimes you'll get a bluish shaded head, which can be called blonde, and that's when two copies of the blue gene come together. So the color itself does not breed true, and that's important when we come to choosing the progeny that we want to exhibit or not exhibit. Just a little jam, so we're just going forward again. The next example that I want to talk about, the genotype of, is the breed the Saxony, which is a version which could be called a trout phenotype with double blue, or an apricot trout is how this phenotype is called in some other breeds. And so it's the mallard base with the light phase and two copies of the blue gene. So the color will breed true because you have two copies of the blue gene. But again, you can see how that effect of blue varies depending on the background of the bird it's in. But so again, if you're thinking about an apricot trout runner, this will give you some idea of how you might go about breeding those if you didn't have them, or how you would go about maintaining them if you did, or where you might go to cross to improve type. Another example, and this is a rare breed, but is the Abercut Ranger, and this is an example really of the classic silver color pattern in ducks. So it's a harlequin phase in the mallard series on a dusky background there. So it's the silver form. And if we add the brown to that, so the brown dilution, you can see the lightening of the head and the brown speculum here, we get the Welsh Harlequin. So you can see how adding gene after gene changes the effect and the expression of these as we go along. And the final example, I think it is anyway, that I want to go through is the example of a magpie duck or the magpie colour pattern in, say, call ducks. And so I know there are people in Australia working on the magpie breed and the magpie colour pattern. And so what we have here is basically a black duck that is bibbed and has the pied or runner gene. So this is the sort of recipe, if you like, for going about that. And the actual pattern itself and cleanliness of it breaks down quite quickly if it's not kept under selection, but that's the basic recipe to go about making it. So I just want to summarize that if we think about these basic building blocks again and ignoring, say, white or blue or brown or buff for a moment, but just looking at the basic colors and overall names are, is if we go through a mallard with the basic wild type allele at the mallard locus. If you've got the dark phase, then you are a mallard coloured bird. If you have the light phase, you're a trout coloured bird. If we think of the mallard restricted allele here, in the light phase, you're the apple-yard coloured bird. In the dark phase, you're with the dusky allele, you're a dusky, and with the harlequin phase on the dusky, then that's the silver type. So a silver call duck, for instance, or the examples that we talked about back with the Welsh Harlequin and the Abercut Ranger. So I just want to point out again and remind people that we don't know what's under white or black. So if you go to the process of crossing one of these coloured pattern birds with white or black, this explains why you don't always get the result you want, and you can change to some of these non-standard color patterns. And then the other element that I think we're seeing in Australia is that when people are crossing breeds and thinking about improving, say, harlequin runners and crossing to trouts, we see some of these off-type color patterns that are coming out. So I think if you're going down those paths, it pays to really understand a little bit more what some of the impure types are to try and have a look at how to ensure the purest version of the genes in those backgrounds so that you're getting your birds true to type when it comes to color. Obviously, how much a judge will punish a bird or penalize a bird, a better word, for some of those color misdemeanors will depend how much the judge knows about it, how good the type of the bird is generally, and also what other competition is there on the day. But with this kind of understanding, and it is a little bit complicated, it does give you, I think, some tools to try and understand that. Or, of course, you can just stick to white and as long as you maintain those 2 copies of the recessive white, uh, you don't have to worry about these things. But I think we all know that some of the color patterns in ducks are really quite beautiful, and when we get them right, they really do stand out in the show. Yeah, my computer's just, there we go. And there is a lot more, and I just want to try and keep within this sort of half hour, 45 minutes, and give some examples. As I said, I haven't kept some of these breeds, and I wouldn't say that I am the world expert on duck color genetics. I just enjoy reading about this and improving my knowledge a bit. So I want to share a little bit with you. As I said, there are some specific genes such as barring and others that are in scabies. The basic principles are the same, but I thought rather than try and go faster than I already have and cover the mosquitoes of things as well, it was better to leave that for another day. Of course, there are many other breeds and colours that we could go through and try and put the genotypes of, but there are online resources that are good. There are some books. So if I didn't cover your breed or your specific colour pattern tonight, there are some resources out there that when you go back and understand the Mallard series and the phase genes and some of the diluters, you can then start to get a better understanding of how it goes together. There is also an online duck genetic calculator if you want to play with that and put some different crosses in and see what you might get. The other element that is important is that there are some unknown or poorly defined modifier genes that are out there that change some of how these major genes I've talked about tonight affect things. So we discover more about those regularly, but unfortunately, the sort of genetics of color are not commercially important so much. So it tends to be other exhibition breeders who try and work out what some of these modifiers do that crispen up the patterns or define things more clearly. And so I think just as with landfowl, it's that sort of package of some of these other modifiers that when we start crossing, we lose some of those. So they are important. It's just hard to, because, well, obviously it's very hard if they're unknown, but even when they're poorly defined, hard to know what's there and how they actually work. But we do know that there are things there we don't understand that add to final product. And I want to thank the people who have put photos online that I've been able to use for this. The majority have come from the group that we're talking in today, and I think just having those pictures, even though from time to time the color pattern might not be perfect or the type of the bird might not be perfect, it just helps illustrate the effects far more than just the mathematical side of things. So I'll leave that there on about the 60-minute mark of presentation, and I'll try and answer any questions that pop up in my comments. I will say sometimes whether it's my bandwidth or others, the comments don't always come up straight away. So they do appear online, and I'll try and get back to them if I do it right now in the presentation. There are a couple of books out there, one of which was the one I first bought when I was trying to think about duck genetics, was one called Colour Breeding in Domestic Ducks by Mike and Chris Ashton, that's available online. But some of the basic principles that are in that, if you just do a Google search for duck color genetics, you'll come across in a couple of forums and other places where people have also tried to summarize this. I think with respect to your comment, Jeremy, with respect to beginners, I think What I'd suggest is either that book or some of the online resources, and try and stick with the sort of major elements first. I think where some of it gets really confusing is when people are trying to understand what's happening in some of the miscoloured Welsh Harlequins or miscoloured Elizabeth ducks or others. And there's some really skillful people who are trying to unravel what they're actually seeing in those populations of ducklings that they're looking at. But if you haven't sort of got those basics stuck a little bit in your head, it's easy to get lost in, or I found it anyway, easy to get lost in that sort of masterclass level. So I think if you try and get the basics right first, it will help that then and enable you to then focus on the questions that are important to you. Okay, I can't see at this stage any other comments or questions. I just uh, have another quick roll down my feed, but it does look like for the moment we're done. As I said, the video stays on the Facebook page, and if you want to type a comment, feel free to do so, and I'll try and follow up if I can. Or one of the great things that other people who have information will chip in as well, and that's one of the ways we learn. So thanks a lot for spending some time with me on a Sunday evening or whenever you catch up, and wish you all well, and we'll talk again soon. Bye now.